going to be a short little lesson on centripetal acceleration. Sounds scary, but it's actually one of the easiest things you might do all year long. So we've talked about forces going left and right. We've talked about forces going up and down. We even talked about forces going diagonal, right? Up and down inclined slopes. But there's one last sort of dimension that we want to look at, and one last sort of area that we can talk about, and that's going around a turn, going around a bend. You might recognize like these sort of examples, like if you take an off-ramp or an on-ramp to and from a highway, you know, you're in a neighborhood and you have to go around a tight turn. This is sort of the things you might experience in a car like this, and we're going to use cars for a lot of the examples because it just makes sense. So I'm drawing here a track for a car to follow, right? Just a nice turn, all right? So here's the path the car is going to take. This dotted line, this path right here. We know velocity is a vector quantity, so velocity is the direction. So the velocity is pointing in the direction of the car. So keeps going, keeps going, keeps going, all around the bend, so on and so forth. So these little arrows are our velocity, right? So a car, and in this example, just anything, any sort of thing going around a curve, feels what's called centripetal acceleration as it goes around a curve. Centripetal acceleration, and then I'll show you the formula for that in a little bit. But as it's going around this curve right here, there's two things acting on it, and really, when you think of the car, it's really one thing that's keeping this car from flying straight off in there. That's the friction of the tires on the road. The tires hold the car steady so that the car can actually make the turn instead of flying off the road going straight. Because when you think about it, if there's no friction and this car wants to make this turn, well, it doesn't matter how you turn the wheels, the car's just going to keep on going straight if it started going straight. It goes back to Newton's laws, right? F equals ma, any action equal an opposite reaction, opposite force, you know, stuff like that. So the cool thing about this is that when an object is going around a turn, right, the velocities are turning with it, but the force that the object feels, the centripetal force, is actually pointing inwards, directly to the center of the radius, right, the turn radius. You guys should know what radius is. It's right, it's the center, and it's how far out it is from the center from each point. So as you're going around this turn, your velocity is changing each second because the force is pointed inwards, that friction that's keeping it there. And you're feeling what's called centripetal acceleration. And we can write that like this. We say AC is equal to our velocity squared over our radius. And that's it. So this centripetal acceleration is the acceleration you feel going around this turn. It's the acceleration because of the turn. You might recognize this if you're in a car, right? You ever played the game Gravity, where you're sitting in the back row with your brothers and your sisters or whoever. Somebody turns the car really hard, and you all slam into each other. You're feeling that centripetal acceleration. So I've attached a quick worksheet. You should be able to do it no problem using this formula right here. This is all you need. So go ahead and try that.